All right. We are ready to talk about the control unit. So last time we met, we were talking about MIPS data path. Essentially, what are the hardware components that we need in order to support the MIPS instructions? And the MIPS instructions that we were looking at were a very small set: branch when equal, add, subtract, load word, store word. Today, what we are going to do is include some more instructions. We are going to include jump instruction first, then talk about the control unit, because there has to be some hardware that is able to look at the opcode field of the instructions and also the function code field of the instructions and tell all the muxes to pass one thing or the other, and also the ALU to perform add operation, subtract operation, and so on, right? So we need actually two control units. We're going to call them main control and ALU control. They'll have a different, they have their own purpose. So this is a quick recall. This is the single cycle data path. It supports the 5 steps, right? What are those? Fetch instruction, decode instruction, fetch operands, execute instruction, and then housekeeping, increment program counter by 1. So it includes all of that. So things like starting from instruction memory, you're going to read the instruction, whatever that instruction is, identified by the program counter. You read that instruction. If you need some registers, you will have to read the register file. You will have to go through an ALU to perform the operation. Then you will have the data memory in case you want to load or store word. Then you may be interested in writing some results of either some ALU operation, or you may be interested in writing something from memory to the register. So for that, you have that write back path, right? So all of that was discussed in the last class. And after every instruction, you're doing this, right? A PC plus 4 and then go back. And you also have this separate circuit here for the branch address calculation. So shift left by 2, add PC plus 4, and go through a mux. Now, Zach asked a question on Piazza, I think, about PC plus 4. Right. So why PC plus 4? Why not PC? So you see the calculation is this, right? PC plus 4 plus blank address, right? Branch address. So suppose the branch address, and think of it in terms of a loop, right? Satisfies, doesn't satisfy. Think of it in terms of a loop. You're always looking at, if it satisfies, jump to this branch address. If it doesn't satisfy your branch address, think of it as becoming a 0. Then it's going to be next, PC plus 4, right? So think of it happening in a loop. If it happens, you jump away from PC plus 4, because if you didn't, you would jump to PC plus 4, which is the next one, right? You are essentially jumping away because you are already executing PC, right? So the branch instruction is at PC. You have already executed that. Now you're trying to understand what is the next instruction. There are only two possibilities, either PC plus 4, which is the next one, or the next one plus something. You see that? Because, so all of that to say, if branch address is 0, then you're executing the next instruction. All right, next, let's see. So that was last class, right? Now let's add jump instruction to this. And while we are adding jump instruction to this, we are also going to add 2 more blocks. I'm going to spend quite a bit of time talking about the blocks. One is the main control unit, which appears over here. Then the other is the ALU control unit that appears over here. We'll talk about those two later on, but first let's talk about the jump. How are we including jump? Remember, there are 3 types of instructions, R, I, and J. Jump falls in the category of J-type instructions, which have only one format. What is that? 6-bit opcode field followed by a 26-bit address. So that address, which is the least 26 bits, is right here. What you're doing is you're looking at the program counter, you're accessing the instruction memory. Once you access the instruction memory, you have got a 32-bit instruction. Out of those 32, the first 6 are opcode, but all the others are your jump address, right? All the others corresponds to this, right? So that's your 26-bit jump address, part of the instruction. With this, what do? You go from 26 to 28, then you pad it up with the 4 most significant bits of the program counter. That's exactly what we are going to do. 26 multiply by 4 by shifting left by 2, you get 28. Then you take program counter plus 4, right? You see this? This is program counter. This is 4. You get PC plus 4 as the output. And if you take the 4 most significant bits of that and pad it up with the jump 28-bit address over there, that gives you a 32-bit jump address. So that's what your program counter is going to get updated with. How are we doing that? We take that 32-bit jump address and go into a mux. And with this mux, you are either picking up the 32-bit jump address or this. What is this? This is coming from another mux in which you have either used PC plus 4 or the branch target address. So you see there are 2 muxes over there. The first mux over here is selecting between PC plus 4, normal operation, and the branch instruction, right? Branching away from PC to support the branch when equal and branch when not equal instructions. The other mux is whatever you selected earlier with jump. So there are 2 selections happening over there. And then whatever gets selected finally, that's what gets updated as the new program counter. So that's how we are adding the jump instruction. Questions about this? How we add jump to this? Good. Of the jump address. Yeah. So jump address, you have got 26. Then you move to left. You have got 28 now. The first 4 come from PC plus 4. So essentially what that means is when you do that jump, you are doing that jump relative to current program counter because the 4 most significant bits are not changing. Next. Now let's talk about this. Let's talk about the control that we can add to support jump instruction. You see, the 6 most significant bits of the instruction, what are they? They are opcode field. Can I say that? That's a for 6 for any instruction, right? R, I, J, all those instructions, for all instructions, those 6 bits are always opcode. So using this input, using this as the input, this control block generates all these control lines. What are they? Register destination, jump, branch, memory read, memory to register, ALU opcode, memory write, ALU source, register write. Some of these control lines might seem familiar because we have seen them in data path. Actually, in the last activity, you guys computed many of these to support one of the instructions, right? So let's see. For jump, what is going to happen? This control block is supposed to look at this 6-bit field, and if it is a jump instruction, it is supposed to activate this line, jump. And that line is going where? That line is essentially functioning as the select line for that mux. So that means if it gets asserted, you will pick up the 32-bit address that you had computed just now. See that? So data path, control, both of those combined, you have your computer architecture, right? So this one, we are adding control. Next, let's quickly talk about the other ones. some of the other ones. Register destination, what is that? Register destination is essentially a control for this mux over here. What does that differentiate? That differentiates between R-type instructions and those I-type instructions, right? R-type, you have got RS, RT, RD. In I-type, RS, RT, RT. The third input is also RT, right? So you are either, so this is same, RS goes through, this guy goes same, RT goes through. However, for the third input, write register, it could either be RT or it could be RD, right? So that's how we differentiated between R-type and I-type instruction. In other words, whenever you're trying to write to a register in the register file, that register could be an RT register or it could be RD register. Can somebody tell me when is it going to be RT? When, for which instruction a write register is RT? Go ahead. I-type. Okay, give me an example. I'm writing to a register. Add I. Yes, add I will do it, right? Add I, that's an R-type instruction, but add I will do it because you have RS, RT, the opcode is your 16-bit immediate. You will add and then you will place it over there. So RT, that will work. What else? Load word, right? Load word will also work over there because you are going to take something from the memory and then put it in the register file using that. So for those, these are examples where write register, your third field is RT. Some examples of instructions where it is RD, add, right? Like add, subtract, all of those R-type instructions in which you have those three fields. There, this write register will be this guy. 5 bits. Okay, so that's your register destination. We talked about jump. What about branch? Branch is going to be a control for branch or don't branch, right? So that's going to support your BEQ or BNE instruction. Where is that going? Branch control is actually going into an AND gate. The other input of the AND gate is the 0 result. Why is that? Suppose you are trying to compare two registers. You subtract one from the other. If it is 0, then it will activate the AND along with the branch. Both combined, you will go over here, so that if you pick up one, you are picking up branch address instead of PC plus 4. Sorry, not branch address instead of PC plus 4. I should say PC plus 4 plus branch address instead of PC plus 4. Right? Because this guy over here is PC plus 4 plus branch. Over here is PC plus 4. All right, let's see. So there was branch. Memory read, memory. So let's talk about memory read and memory write. So memory read and memory write, let's see. This guy here and this guy here, those are for memory accesses. In some cases, you want to write to memory. Some cases, you want to read from memory. Say load word, store word instructions. So those are the two control lines for that. The common question I get for this is, can both of them be active at any given time? No, they cannot be active. Both of them cannot be active because one, you're trying to access memory, right? So it's a single cycle data path that we are looking at. If you're trying to write to memory at the same time, you cannot be reading from memory. If you want to read from memory multiple times at the same time, multiple things, sure, you can do that. So you can read, but because you are writing, you cannot read at the same time. You have to separate them out in time. So they cannot be one at the same time. They can be 0 at the same time, sure. Because I don't want to do anything with the memory, leave them unasserted. Next, memory to register. That control line is coming out from here and going to this mux. Can you guys think of an instruction in which memory to register is a 1, needs to be a 1? Go ahead. Load word, right? So if this is load word, you read a word from here and then you put it into the register file. Add would be an instruction for which memory to register would be a 0, because there are two things that you are selecting from. One, things that you just read from the memory, or the output of the ALU. Right? So in your add, say you added two things and you found out the answer and you want to write it back to the register file. In that case, you will have memory to register as 0. Next, ALU op. ALU op, as you can see over here, is a thicker line. Right? So the example that we are going to look at today is with ALU op field having 2 bits. So it's a 2-bit field. What is it going to do? Well, it is going to give you some indication. It is going to give the ALU some indication about what to do, right? So it's not directly controlling ALU, right? So for example, this guy is not directly going in here. It is actually going into this ALU control block. So there is some ALU control block which takes in this opcode field, ALU op, and also the last 6 bits of the instruction. So what are the last 6 bits of an instruction? Everybody says it depends on the instruction. What is it for the R type? For the R type instruction, the last 6 bits are function field, right? For I type instruction, it is part of the immediate field. For the J type instruction, it is part of the jump address. So different types of instructions, it means different things. However, those 6 for R type specifically correspond to the function field, which essentially takes care of variations of the same operation. Add U, for example, right? So you're looking at this ALU control block, which is going to take 2 bits from here, it's going to take this function field from here, and it's going to generate a 4-bit code telling the ALU what to do. Add now, subtract now, whatever that operation is. And now, or now. So ALU will get a 4-bit output depending on this being 6 bits, this being 2 bits, this being 4 bits. And question is, we need to design this, right? We need to design a logical control block that will take in 6 bits, 2 bits as inputs and generates 4-bit output. We also need to do this. We need to have some logical control block there that will take in a 6-bit opcode field, which is for all instructions, and be able to generate all these control lines. Right? So that's sort of our goal today. How are we going to do this? We talked about memory to register. We talked about ALU. We'll go into it a little bit more. Memory write, we talked about ALU source. Okay, ALU source, simple. ALU source is over here. It is either going to pick up whatever you just read from a register, for example, an R-type add instruction, right? Or it might pick up whatever you just extended to 32 bits. For example, add I instruction, right? So depending on one or the other, that's your ALU source. From the register file or from a 32-bit sign extended constant. Register write, even simpler. Are you writing to a register in the register file or not? If you want to write it, make it a 1. Don't want to write it, make it a 0. An example of an instruction where you want to write and don't want to write. Let's start with when you want to write. Go ahead. Load, right? Load word, you have to write to a register. So that would be a 1 there. An example of when you don't want to write. Store word. All right. So store word, you don't want to write to a register. So register write control would be a 0 for that. All right. Questions about this? I think we have covered all the things that I wanted to cover. Once, twice. Okay. So here is a table. This is from the textbook, and it is essentially doing the same job as we just did. It is telling us for all these control signals, register destination, write, ALU source, PC source. Oh, by the way, PC source is not over here, right? So PC source, essentially what this guy is, PC source is another control that is computed. This is actually, hold on. So PC, I'll show you guys in a different diagram here. PC source is over here. So the output of this is the PC source. So PC source is a control line that is not directly computed by the control unit. It is actually the result of branch and the zero result here, right? So slightly different from all the other control lines, which are directly the output of the main control. Did I talk about main control versus this? All right, let me make that differentiation here. Main control and ALU control. Okay, so we can go through this table exactly the same way as we did, and we can have a very long discussion about these things. Let me just point a couple of them. So for example, let's say register write. What is the effect when it is deasserted, meaning inactive? When the register write is inactive, there is no effect. You are not writing to the register file. But when it is asserted, you are writing to the register file. What are you writing to the register file? Whatever is at the write data input. Write data input along with write register identifier, both has to be there, and then you make write register 1, you will be able to write to a register in the register file. Another one, let's say memory to register. What is the effect when it is deasserted or inactive versus active? When it is deasserted, the value fed to the register is coming from the ALU output, ALU result. Or when it is asserted, like the name suggests, memory to register, going take the thing from memory and allow it to go to a register, right? All the others are there for your reference, but if you guys have understood all the things that we were talking about, like these signals, that's just written up in words in this table here. Anybody needs me to go into any one of these things? Is any signal bothering you guys? No? Okay. So we are adding control, right? That's what we are doing in this chapter. We are adding control, we are adding main control, and we are adding ALU control. And our goal is to select the operations to perform. What arithmetic or logical operations should I do? Am I doing read or write operations? And so on. I'm trying to select those operations here. But also, all our control signals that are coming out of the control blocks, they are also controlling how the data is flowing through our data path, right? Because essentially we are opening this tab here and then closing that tab there, opening that. So we are essentially allowing the data to pass in the desired path to support our instructions. Information is coming from 32 bits of the instruction. Essentially, it's coming from two fields, opcode field and the function field. Opcode field applies for all the three types of instructions, R, I, J. Function field only makes sense for the R type instructions. Function field is an input to the ALU control block. Opcode field is the input to the main control block. An example here, add 8, 17, 18. What does it do? Takes the contents of register number 18 and 17, adds them up, puts the result in register number 8. Destination first, right? So your opcode field is 0. How do we know? How do we know that the opcode field for add is 0? All zeros, 6 zeros. Look at the MIPS reference sheet. You look at the MIPS reference sheet, you will be able to see that add is all zeros. RS, RT, RD, this should be a refresher, you guys. This is 8, so 8 for RD. This is 17 RS, then 18 RT. No shift, and function field for this is 1 followed by 5 zeros for add. Again, who tells me this? The MIPS reference sheet tells me that. So what we have is an opcode field over here and a function field over here. Those are highlighted. Those are going to be inputs to our main control block and ALU control block. For the main control block, it is this. Input to main. And then we have this guy as, oh, input to ALU control. Only makes sense for the R-type instructions. So here, the question that you guys should be asking yourself is this. Given the 6 bits in the opcode field, you have to design a circuit that will generate all these guys. Right? If I tell you what this is, you have to design here so that you generate all these guys. Right? And if I tell you what this 6 bits is and this 2 bits is, you have to design something here to tell me what these 4 bits are. Right? So that's where we are going with this. All right. This is, again, repeat. The control unit is combinational circuit. 2 parts, main control, ALU control. Main control is over here to generate all the control lines. ALU control is over here. Essentially generates a signal to let the ALU know what to do. Here, which instruction is not being supported in this diagram? There is a particular instruction that we had included, which is not being supported here. What is that? Good. So the branch is included, right? Branch is sort of over there. But in the list of instructions that we had, 8 of them that we considered, we had branch when equal, and we are doing that. We added an instruction today, jump. It's not there here. Jump instruction is not being supported by this, right? Why am I talking about that? The reason is this. Because the data path along with the control unit can be an overwhelming amount of detail in one particular figure, sometimes in textbook or in slides, you might see something get omitted, right? So over here, the focus is on the control block, so that's there, but jump is not in focus, so that's conveniently dropped from this block diagram. And that will happen with these diagrams more and more. So you have to be aware that, yeah, it is there, but it's not being shown here, just so that things can be a little bit cleaner. Right, next move on. Okay, so we'll start with our attempt to design that ALU control and the main control combinational circuits. They are combinational, right? Why is this combinational circuit and why is this combinational circuit? For a given input, there is only one output, right? So you give me a 6-bit, I'll give you all the other bits, whatever they are. Same applies for ALU control. So they only need to be combinational, no sequential element required. Next, controlling the ALU. ALU control depends on instruction. We are going to define a set of 2 intermediate control bits called ALU op. What are these? These are essentially the output of main control. And they also function as input to ALU control. That's why they are intermediate. They are output of main, but the input of the next ALU control block, right? So this is right here. Output of those guys, but input of this ALU control. So that is your ALU op. 2 bits. ALU op 1, ALU op 0. They have a specific meaning. If they are 0, 0, then the meaning for 0, 0 is defined by MIPS ISA. Do an addition at the ALU, but that addition is supporting load or branch. Remember, for load or branch, we need to add what? Base address to the offset address, right? To compute the target address, we need to add. So as the differentiation is this. ALU adds. It can add for add I, it can add for add instruction, it can add for load word, it can add for store word instruction. All of these places the ALU is adding. But we are trying to differentiate between add that happens for R type and add that happens for I type and add that happens for specifically for load word and store word. So for load word and store word specifically, ALU opcode fields, ALU op 1 and 0 are 0 and 0. Because it is a specific I type instruction, right? The function code doesn't matter here. It is a specific I type instruction for which we need to add. Next, when ALU op 1 is 0 and ALU op 0, the least significant bit of that ALU op is 1. What are you doing? We are doing a subtraction for the branch when equal. It is not the subtraction for subtraction, it is subtraction for branch. So the ALU, as far as the ALU is concerned, is still doing the subtraction. However, it is an I-type instruction for which there is no function field. So we are trying to differentiate that subtraction with this with ALU op field. So subtraction for to support the branch when equal, because register 1, register 2, subtract them, find whether it's 0 or not. Next, 1, 0. When the ALU op bits, the 2 bits are 1 and 0, then we are going to look at the function field that specifies the specific R-type instruction. So now we are going to look at, so whenever it is 1 and 0, you know it's a R-type instruction. When it is 0, 0, you know it is a I-type instruction for which you are using add to support load or store. When it is 0, 1, you know that it's a subtract operation to support branch when equal. Go ahead. So I-type instruction add, we are going to use, so I don't think our 8 instructions, we are supporting that, right? Let's see, hold up. Let me see if R-type instruction, right, so that's not included in our data set for now. What that means is you are going to have to look at a general case where you have a bigger data pad to consider in that case. For add I, what are you doing? For add I, you are looking at addition of a register. We are going to get that from the register file and the 32-bit sign extended value, right? So once you have this from here and this from here, oh, in that case, you are going to treat add I as far as ALU is concerned as a R-type instruction. Because once you have determined this and you have picked this up, you have a 32-bit over here. So it's very similar to a R-type instruction there. Next. Now, when you go into the function field, which is for R-type instructions, here are your R-type instructions: and, or, add, subtract, set on, less than. So for that, you have got a ALU input of these things, arbitrarily assigned: 0, 1, 2, 6, and 7. So here is the thing. You have a 6-bit function field that is made up of the opcode fields and the input field. The thing that we are trying to answer is, if we know this function field here, and if we know the opcode fields over here, can we generate the 4-bit output here or not? Similarly, for the main control, if we know the 6 bits over here, can we generate this or not? So now let's take a look at this table. Hopefully this will sort of give us a better idea about what needs to happen. On the left, we have the instruction opcode or instruction mnemonic. Load word, store word, branch when equal, and then followed by all the other R-type instructions. For load word, store word, and branch when equal, we know that the ALU op fields should be those 2 bits, right? 00, 00, 01, given by our lookup table earlier. Then for the last one, which is for R-type instructions, we know that the ALU op bits should be 1 and 0. So all of these guys are 1 and 0 here. Yeah. Next. What is the operation? Load word here, store word here, branch when equal here. This is add, subtract, and, or, set on, less than. Next. Function field doesn't matter, doesn't matter, doesn't matter. Why is that? I type, I type, I type. The last 6 bits are part of the immediate constant, so it doesn't matter there. However, once you get into this function field for add, subtract, and, or, and, set and less than, then the function field is going to matter, because the last 5 bits are the function field. Last 6 bits are the function field. So here, how is that constructed? You see, the 2 bits of the function field are actually the 2 bits coming from here, ALU op. So the first 2 bits of that function field are directly 10, because 10 is for R-type ALU op. Followed by the last 4. The last 4 are essentially coming from these guys, the lookup table that we had here. If you want to do AND, ALU input should be 4 zeros, or 1, or 2, or 6, or 7. Those are coming over here. Then, no. Those are coming over here. These are from the lookup table here. Next, we need to design that circuit, whatever we have, that will take in these 2 bits from here, these 6 bits from here, and be able to generate this. The other 4 bits over here, where are they coming from? They are coming from our sheet, right? Let's see. Right. So that is coming from our MIPS reference sheet, whatever that 6-bit code is for add, subtract, and, or, and, set on, less than. Here we are doing add. Here is your ALU control input. For add, we have got 0010 because add we have got 0010. All right. So whenever we need to add, here, not the last one. Our ALU control input is going to be the same, 0010. Whenever you need to add, we need to give the ALU input a 2. That 2 is here, here, and here in our small set of instructions that we are trying to do. All right, so let's see. Let's talk about the PC source. How are we generating all the other control lines versus PC source control line? Slightly different. PC source control line is not directly computed by the 6 bits of the opcode. It is actually computed separately. Where is that? PC source is being computed. That's the only control line that is computed way over here. So it is the output of the branch ANDed with the 0 result of the ALU. All the other control lines are directly the output of the main control unit. Come back. Okay, so, that's that. Then we have this table over here, which can provide us with as a very good reference. For R-type instructions, for load word, store word, and branch when equal, a very small set here, we have determined all the control unit, control signals. So for example, R-type instruction, register destination is going to have RD, right? So it has to take 1 there. ALU source should be 0 because it is going to go from the register file to the ALU, right? So R-type instruction, ALU source is 0. We can talk about it over here. R-type instruction, ALU source here should be 0, right? This has to go through. Memory to register, no, you don't have to do that because it is coming from the ALU. Register write, yes, you have to do the register write. Memory read, you don't do memory read there. You don't do memory write over there. You don't do any branching over there. And it's an R-type instruction, so opcode field should be 1 and 0. Right? So similarly, you can compute that for all the other instructions, and you can keep incrementing these instructions there. So for example, load word, I need to do a memory read. Store word, I need to do a memory write. For all the others, I don't need to do memory read or memory write. Once you have this, we can start talking about that combinational circuit that we need to create. So here is sort of the answer here, right? So let's talk about this main control unit first, then we can talk about the ALU control. The main control unit is a combinational circuit that takes in a 6-bit input with the opcode field, right? So that's your 6 bits inputs here, and generates all the outputs for the control lines. Includes, we are skipping over jump over here, but all the others are listed. Register destination, ALU source, all the way down to the 2 ALU op fields. So let's take a look at an example to see whether it matches up or not. So let me look at my MIPS reference sheet here and look at, say, a load word instruction. So a load word instruction, LW, has a opcode field of 23 in hex, right? Load word has 23 in hex as the opcode field. So if I go back over here and say load word, opcode field is 23 in hex. 23 in hex corresponds to what? 0010 and 0011, right? In binary. And I'm looking at it as a 6-bit sequence, so I'll forget about these two ones, these two zeros there. So 10, 00, 11, right? So you see what happens over here. When those bits, by the way, those should be over here, right? So 1, 0, 0, 0, 1, 1, right? when they go into this combinational circuit, all these guys will give you a 0. 0 here, 0 here, 0 here. All these guys will give you a 0 except for this load word. Why is that? You see, this one goes through. This 0 gets flipped. This 0 gets flipped. This 0 gets flipped. So that's the only AND gate in which you actually have 6 ones getting ANDed. All the others will have some or the other thing missing, giving you a 0 at the output. So when that gives you a 1 there, now we need an output logic to compute your control lines. So what is that? Load word. You see, if I look at this table here, load word, 0, 1, 1, 1, and so on, is that getting reflected there or not? Well, this is a 1. That one goes here, makes it this guy into a 1. Come on. Register destination. What is that going to equal? 0, right? This guy is a 0 there. Next, this guy is going to be a 1. Next, you can do this for all of them. Right? So the combinational circuit gives you that code, which should match the table that we had just shown. Right? So for the MIPS instructions that we have included, give the 6-bit opcode field, using the combinational circuit, generate all the control lines, so that appropriate controls can be sent to the ALU and also to the muxes to control the data flow. Next, let's come to the ALU control block. The ALU control block has 2 inputs. One is the 6 bits for the function field meant for the R-type instructions, and the 2 bits from main control, the ALU op. Depending on what these guys are and what these guys are, I need to generate a 4-bit output that goes to the ALU to let the ALU know what to do. Options, if it is 4 zeros, do an AND. If it's 1, do an OR. If it is 2, do an add or subtract or set less than. Those are the options. Those go into the, where is this? ALU input, right? So where is that going? It's going here. So be a little bit careful about this. ALU input is different from the inputs to the ALU, right? So the inputs to the ALU are actually coming from either the registers or the 32-bit sign extended constant. This is the ALU input control, right? So this is sort of telling the ALU what to do, a 4-bit code, which is based off of 2 bits from here and then 6 bits from here. So let's see if that matches up here. If what is operation 3 going to be? Take ALU of 0 and its complement and it. Always going to be 0 there, right? X and X complement, right? The same thing getting complement. Always going to be 0. Let's go back and check. The least significant bit, the most significant bit of the ALU input, always the 0, right? Maybe a slightly thinner line would have done it. Yeah. Next. Opcode 2. This is ORing off this guy. Sorry. We need to AND this with that guy F1 and here let me do this. They are F0, F1, F2, F3. So there are two most significant bits are not mattering here. Why is that? Because they're always going to be 1, 0, right? Either for the R type instructions, they're always going to be a 1, 0 there. So here you have F1 ANDed with ALU op 1. Take these, OR it with ALU op 0 to get operation 2. Now let me ask you guys like a zoomed out question here. How would you design this? Well, you would go back and look at it as a truth table, right? Bits here, I've given you what the output should be, and then you would go do K-maps or whatever to come up with the circuit over here. So that's how this circuit is computed. Yeah, go ahead. Oh, say that again. Yes, always be a 0. Always a 0, right? So because we are hardwired this and this, so the same thing is being hardwired. So the ALU operation here, 8 instructions, going to expand to a lot more instructions. So to understand our smaller set, we are dealing with all these at a much smaller scale. But when you expand it to all the integer instructions as well as floating point instructions, it's going to start mattering over there. But yeah, over here, operation 3 doesn't play a role there. Next, let's talk about delay. Now, when we start talking about delay, it is in the context of speed at which your MIPS ISA computers, MIPS-based computers can run. Because it's made up of hardware, right? So you have, say, components such as memory, ALU and adders, the register file, and all the other components. Let us say that we associate a speed through the memory as 2 nanoseconds. So if you are trying to do like a memory access, read or write, it's going to take you 2 nanoseconds to do that. ALU add and adders going to take 2 nanoseconds. Register file is going to need 1 nanoseconds for either for reading or for writing. And all the others, so let's say wire delay, muxes, all the others are all negligible. If we take that into consideration, if we assume that these components have so much speed, next we need to start talking about for supporting R-type, I-type, J-type instructions, how much delay is involved to support those instructions. So for example, R-type instructions, what are the components that are used? I need to do an instruction fetch for all the instructions, right? That stage is going to be there no matter what the instruction is, load word, store word, branch. For all of them, I need to do the instruction fetch, which means given a program counter, read the instruction memory. That's going to be there all the time. After that, there is going to be a register access. Essentially what that means is, once you have the 32-bit instruction, you are going to need to look at the register file for reading, right? So the first time you are doing this register access, you are doing the reading everywhere. So for example, if you are doing the add instruction, you are trying to read 2 registers at once. If you are doing an add I instruction, you are reading only 1 register there, right? But you're reading. The register access for the register file at the beginning is for reading. Then what are you doing here? After you read the contents of a register, maybe the second operand is constant, or it may be coming from the register file itself. The next one is the ALU, right? So if I go back and look at a good diagram here, say here, right? Fetch is happening here. We just read the register file here. Then we are going to go to the ALU there. Then we are going to have a memory access there. And at the end, we may have to write things back over here. So sometimes we may have register access later or not, depending on the instruction. So if I go back there, see, okay. So ALU is going to be there for all of them. It's going to be working differently. For our type instruction, it is actually performing the arithmetic or logic instruction operation. For load word and store word, why do we need to use the ALU? Word. For the for the target address computation, right? Base address plus offset. We need to do that over there. For branch, I need to use the ALU to subtract, right? To compute the zero result, whether active or not. So components used, ALU, all of them going to be there. Next, for R type instruction, after you finish with the ALU, you don't have to go to the memory. You can directly go to the register access. This time for writing it back to the register file. But for load word and store word instructions, you will have to do a memory access there. So can you guys tell me what is this going to be and what is that going to be? Say for load word, what should I write? Memory access should be read or write. Read there, write there. Yeah. And once I write to memory for store word, I'm done, right? That completes the operation. However, for load word, after I read the memory, I still need to do the register access. Why? Because I need to still write it to a register, right? So what all of this means is, depending on the type of instruction, your delay is different, right? Because each of these is corresponding to a delay. We have talked about delay through memory, delay through ALU and adders, delay through a register file. We have associated a delay, a different delay with each component. So now that we have understood that each instruction might have different stages that it goes through in total, the delay is going to be different, right? Which one is going to matter? The worst case is going to determine our best clock rate, right? The highest clock rate we can associate our MIPS architecture with is going to be dictated by our slowest instruction. So let's see what that turns out to be. So let's start with an R-type instruction. For R-type instruction, we just found out that we need to do a register. So fetch, register access, ALU access, and register access. We talked about that, right? So we said fetch, register access, ALU, register access. That's what is involved in the R-type instruction. Fetch happens where? Here. 2 nanoseconds added. Yeah, because we said, what is that? Memory, right? Memory access, 2 nanoseconds. We added that. Next, after the instruction gets fetched, what is the next one? Register access, which means I need to read the register file. What is the register file? 1 nanosecond. Add that. Next, after you read the register file, go through the ALU. What is the ALU delay? 2 nanoseconds. Add that. After that, register access for writing. Go back 1 nanoseconds for writing into the register file. So you add up, it takes 6 nanoseconds, assuming these delays through these components, takes 6 nanoseconds to finish a R-type instruction, right? How about for load word? What we are doing over here is delay analysis, essentially figuring out what is our slowest instruction. So for load word instruction, what is going to happen? For load word, we need to do these things. Fetch, read register file, ALU, read memory access, read memory, and then write register. So you have got 2 for the, let me just draw arrows there. 2 for that, 1 for that, 2 for that, 2 for that, and then we come back and do 1 for that. Add up, this guy is going to have 8 nanoseconds. 2 nanoseconds slower than an R-type instruction, a load word. How about store word? Store word, 4 steps involved over here. Fetch 2 nanoseconds, register read here, which is 1 nanosecond, ALU to memory, write 2 nanoseconds. 7 nanoseconds in total for store word. We've got 6, we've got 7, we've got 8. For branch when equal. Now, for branch when equal, there is going to be multiple paths that we have to be careful about this. So, branch when equal, what are we trying to compute? One, we are trying to compute PC plus 4. That's one option. The other option is PC plus 4 plus branch address, right? So, PC gives us the instruction memory, right? So depending on the program counter, we look at the instruction memory to see if it is branch or not, right? That's what the instruction is. That is going to happen. And at the same time, because it's a branch when equal instruction, we need to also do, so that's, this PC plus 4 happens at the same time. For all the other instructions, it is just PC plus 4, but for a branch when equal instruction, it matters now. So we need to pay attention to that because it could be PC plus 4 plus branch address. So that 2 nanoseconds and this 2 nanoseconds is happening in parallel. So we don't need to do this plus this. They are both happening at the same time. So that's 2 nanoseconds there, right? Next, if these are the 2 nanoseconds over there, then what is going to happen? Once we have the instruction, it turns out to be what? A branch when equal operation. For branch when equal operation, what do we need to do? Fetch, we already did that. We need to do a register read. Okay, we need to do a register read. What are we going to have for a register read for a branch instruction? We need to compare the contents of the two registers, right? So we need both the registers. All right, so we need this 1 nanosecond added over there, right? Next, what is going to happen? Need to subtract them. If you need to subtract them, you need to use the ALU. That is going to add another 2 nanoseconds there. But this 2 nanoseconds over here, what are you computing? We are computing PC plus 4 plus branch address. Both the inputs must be present at the adder so that it can work, right? You need to have an input from this guy here, right? Once you get the 0 result here, that is going to dictate what we pick. But here you have PC plus 4 that's going over here. The other is directly from here. What is that? PC plus 4 plus whatever the branch address is. So both inputs should be present over here. PC plus 4, PC plus 4 plus branch address. You guys see that? The branch address is computed over here. So you've got 2 here, 1 there, and 2 there. Hold up, what am I missing here? So PC goes to the instruction memory, read the instruction. At the same time, you compute PC plus 4. So that is ready after 2 nanoseconds. This is being read after 2 nanoseconds. Then we go to the register write destiny, where we are going to read for 1 nanosecond. So that I have included in my time. So this guy, even though it is ready at 2 nanoseconds, it is meaningless because it is going to have to wait for the other address to come in, right? When is the other path ready? The other path is ready after 16-bit is here, extended no access. So it is ready over here, right? So the only difference was the 2 nanoseconds. Once I have these two guys ready, both inputs must be present, yes. Then I can do the addition over here to compute the branch address. To compute this branch address or that branch address, how much time did it take me? It took me 2 nanoseconds plus 2, 4 nanoseconds there, and it took me 5 nanoseconds over here to compute that. Okay, so total is 5 nanoseconds. Okay, so here, let me take another attempt at this. Program counter tells us what instruction, what is that instruction, right? So you read the program counter. You read the instruction memory at the program counter. When you're trying to read this, that is going to add 2 nanoseconds to your time for reading. At the same 2 nanoseconds time, you are also computing PC plus 4. Was there for all instructions. Both of them are happening in parallel. Next, after you do this, you have computed, you know the 16-bit immediate, right? From the instruction memory, you know the 16-bit, last 16 bits of that field. That is going to be your constant, immediate constant. Sign extender, we are not associating any delay with that. Negligible delay there, negligible delay with shift by 2. So our number to be added to PC plus 4, the branch address, is ready already, right? Once you have PC plus 4 ready over here and this guy ready over here, you will be able to add them to compute the branch address. But they happen at the same time, right? 2 nanoseconds, 2 nanoseconds. This gives you guys, gives you there. This itself gives you these guys, and you will be able to get this. That's ready, right? So that's sort of that arrow that is representing that. Now, so all that is to say, I cannot take this 2 nanoseconds, which is in parallel with this. So 2 nanoseconds there, plus 2 nanoseconds there as my branching time. I need to include this guy because this is slowing me down, right? So longest path is what I should consider. I cannot take the shortest because the shortest would be 2 plus 2 would be the shortest. I need to include this. Why? Because if I did not include this, you see, I'm waiting for the 0 result, right? In order to complete that instruction, I need to wait for the 0 result. Only then I will be able to pass one or the other through. One is PC plus 4 or the other is PC plus 4 plus branch. So if I need to wait for the 0 result, I need to wait for 2 plus 1 plus 2, 5 nanoseconds. You guys see that? So shortest path would be 2 plus 2, but still you are stuck over here because the result is not available after 5. So the longest path over here, which is sort of this, becomes the bottleneck, which is why we need to consider that as our delay analysis for branch when equal. 5 nanoseconds there. Shortest so far, right? So we have got 5, 6, 7, 8. I think we have got all those 4 options now. So for R type, 6 nanoseconds, 8 was for load word, 7 was for store word, and for branch, it was 5 nanoseconds. However, our overall clock rate, the clock rate that we associate with this MIPS ISA, has to be limited or constrained by our slowest instruction, which is 8 nanoseconds in this case. So that will give us how fast we can run this. So this waste would be much greater if we included other commands, right? Like floating point and all the other instructions. Then the discrepancy between the slowest and the fastest instruction would be even more. All right. You guys should be okay with activity. activity, what is that? 9, due tonight. We have exam on Thursday. I've sent out like a sign up on Gradescope for you guys to mark your preference about where you want to take the exam. I didn't take a look at the results because from what I understand, there was a healthy sort of interest in taking the exam in the room, and there were also a lot of people who wanted to take it online. Doesn't matter. I will have exams printed for you. Whoever wants to come to the room to take it, I will have exams printed for you. The benefit of taking it in the room is you don't have to scan and upload. You don't have to worry about camera proctoring and all that. You can just, and printed papers will be there for you. I will scan them into Gradescope for you, so you don't have to worry about that. MIPS reference sheets will be provided. You don't have to print those. So yeah, so you will go ahead. Yeah, you can have your laptop out. Yeah, sure. I would, if as long as you are scrolling through the lecture slides and stuff, absolutely fine. Let's see. For those of you who are online, again, it's an open book, open notes. Even for you guys, if you want to bring in some books or notes, feel free to do that. People who are online, you guys will be required to keep your cameras and mics turned on so that you can be proctored. For you guys, exam will be made available. I have not made a determination yet, but either Gradescope or I'll post it on Piazza. I'll have to think about that, but I'll let you know just before the exam starts or a day before that. I'll post a note on Piazza to tell you guys what's going to happen. But you will need to scan them into Gradescope. For these guys, for the people in the room, you don't have to worry about that. Material that we talked about today is not going to be part of the exam. It's going to be just the lecture 1 through the data path. Right? Until the data path content, that is going to be fair game on the exam. Good. No, doesn't include today. Just includes, because it's just a day before the exam. So as much as possible for all my classes, I try to not include the last lecture on the exam. Sometimes that's not possible, but now it is. Questions? Good. Yeah, so Tuesday, 3 p.m. Tuesday, tomorrow 3 p.m. It will be recorded, it will be posted. I did a similar review session for signals day before yesterday using WebEx Teams. It went well, I think. The only thing is that for signals, I had some logistics and a lot of questions. For CANOS, I don't know how many logistical things I'll have to talk about. There's not much, right? Like, okay, this is the content, this is the logistics, and we are done. So we'll try to have your questions ready so that we can spend some time. If not, that's fine as well. We can end early. So we'll have a review session tomorrow, 3 p.m. In the WebEx team for our class, CANOS General WebEx Team Space. I will send you guys reminders on Piazza and WebEx Teams before it starts. Other questions? Everybody is taking the exam at the same time, right? 8 to, maybe we can go up to 10:15. So I'll have to see if we need to end at 10 or we need to go up till 10:15. But it'll be one or the other. I cannot go until 10:30 because I need to start class over here at 10:30. Extra time. If you have any extra time accommodations, please let me know right away. I have not heard from anyone so far, so it looks like 8 to 10:15 it is, or it could be 8 to 10. Other questions? What is definitely going to be there on the exam? 3 things: C code, MIPS code, machine language, right? Going one from the other to the other, you guys should be like comfortable doing that. Minimizing MIPS instructions. So given one set of MIPS instructions, if you can follow that and say, all right, I can maybe get rid of this and this and this. Rewriting assembly in reduced number of instructions. So questions like that. The calculations, right? The CPI and which one is faster than the other. The numerical calculations, essentially a lot of calculator work. That is going to be part of the exam. Conversions for your 32-bit single precision format, double precision, 64-bit double precision standard, decimal to this or this to decimal, understanding the difference between normalized and denormalized numbers, floating point numbers. And then there will be definitely a question on data path. So I've uploaded a back exam. I got a lot of slack for it when I conducted that exam 2 years ago, or 2 years ago, a year and a half ago. So when you review it, I hope that you don't feel that it was difficult. But spring 2020, when I gave it, I had some very mean eyes in the room after the exam. Still not sure why. It got better after the second exam and the final exam. That was my first time teaching the course, so I wanted to sort of update it the way here students didn't like that. They wanted CANOS to be CANOS. Okay, I think this is it. You guys are welcome to stay in the room. I need to sort of set up shop for the exam that is coming up. I will see you guys on Thursday then.